right. So we are now second half of the day. We're going to be switching over content-wise into our Carnegie Mellon Sports Analytics quote camp student speakers. So the camp, I'll say, is not actually a camp, right? It's more of a pretty intensive 2-month-long summer research program where undergrads from across the country can apply to this program. You can scan a QR code to take you to the page, and they get what I view as like statistical learning boot camp. Get instruction, work on different types of projects, external partners. In the past couple years, these students have been by the one and only Quang Wen, who is a fourth year. Quang is a fourth-year statistics PhD student here at CMU, and he is a 2-time finalist of the NFL Big Data Bowl and a 1-time semifinalist. He doesn't like to talk about that one, but he will be introducing the students to you. So I'm going to turn it over to Quang, and then I'll work the slides here.
All right, thanks, Ron. So our first group, we have PassPredictR, Contextualizing NFL Throwing Decisions Through Modeling Receiver Choice by Zhou from Rice University and Zach Pipping from University of Florida. Oops, we're good. And this project is in partnership with Karim Kassam from Teamwork. So please take it away.
Cool. Welcome back from lunch, guys. My name is Zach.
My name is Lou.
This is our presentation, PassPredictR. We're contextualizing throwing decisions by modeling receiver choice. So with 23 seconds left in the fourth quarter, PJ Walker rolls to his left and throws this bomb to DJ Moore in the end zone, double coverage, touchdown. It's fantastic. DJ Moore celebrates. He takes off his helmet, forces a long extra point, sends him into overtime because they missed that extra point. They intercept Marcus Mariota. They then miss a field goal in overtime and lose the game. It was rough. It was rough if you're a Panthers fan. That being said, we're not going to look at that. We really just want to focus on the fact that he threw to DJ Moore. Obviously, it's a touchdown. It's the right play. It's the right read. It's perfect. However, if he had thrown an interception, would we still be calling this the right throw? That's one of the questions we seek to answer.
Yeah. So as Zach said, this play asked some very interesting questions. Given this really long throw, it's a really risky throw. What would other quarterbacks do in this situation? What do we expect normal quarterbacks to do given the same game state? And given this expected option, which quarterbacks are deviating more from this expected option? Are they more predictable? Are they more unpredictable? In this unpredictability, are they finding success in this deviation? Or maybe should some quarterbacks throw more typical passes? Maybe they should be more conventional. So here in attacking this problem, we're essentially looking to build a ranking model to determine the most likely throw target given the game state.
Totally. So a quick data overview. I'm sure a lot of you guys are super familiar with the Big Data Bowl. If you're not, though, basically we have game and play data. So in the first 9 weeks of the 2022 NFL season, every game, every play that happens, it tells you what happened in that play, what the score is, and just how it changes over each play for each game. Inside those plays, you have more data, which is player play data. It says what each player in that play, the 22 players, 23 if one of the teams messed up, did in that play, what routes each player ran, what they contributed to that play. And then last but not least, we have tracking data, which allows us to not only make these super cool visualizations that you see on the right here of that PJ Walker pass, but it also allows us to construct features and then infer on those features. We obviously wanted to look just at the throw plays. So we got rid of any rushing plays, special teams, got rid of those. Anything that was a spike or a throwaway. We need the quarterback to make a decision to throw to someone. So if they didn't make an actual decision to throw to someone, we just got rid of that type of play.
So yeah, I think a very easy answer to, who's the quarterback going to throw to is just throw to the open man. But that can give us a relatively incomplete story. For example, with this Carr pass to Adams, Carr makes this pass to Adams while Adams is relatively covered at the time of throw, but because of relative distance, because of relative velocities, Adams is able to get free during the course of the throw and get separation and make a clean catch. So here, this leads into us using speed and orientation as our proxy for future separation, since compared to current separation, it's not as important. So here, we're essentially adding the speed vectors to the current player positions, and then taking the magnitude of the difference of those speed vectors. And here we see a pretty strong correlation with actual separation at time of catch, with the correlation around 0.811.
Totally. So that's just one of the many features on the receiver side of things. We also sort of wanted to look at quarterback positioning. And one of the more advanced things that we looked into was trying to derive a quarterback's line of sight. In the data set, there's no variable for where the quarterback's looking. So we sort of had to maneuver and use the orientation and the movement vectors and try to create something that could give us an idea of where we'd expect the quarterback to be throwing. And so using that, you can see this for a Russell Wilson pass to Cortland Sutton. He initially looks to Melvin Gordon, and then right before he makes the throw, we see that shift towards Cortland Sutton. Obviously, we have to lag this, so it's not after the throw. We lag it about 5 frames. But this is one of the things that we were able to create in order to make more features, whether it was angle difference or total distance off of that orthogonal vector.
Yeah, so using these features as well as some other features we'll get into next slide, we essentially treat this as a learning to rank problem using a gradient boosting approach to rank the likeliest recipient at the frame of pass release. So here, after a random high propagator search and 5-fold cross validation with folds on matches to avoid data leakage, we get an accuracy around 59.9%, which is significantly stronger than if you just randomly guess, which gives us around 1 in 5, as well as if we just simply choose the player who has the most separation at time of throw, which gets us accuracy around 31%. So in essence, using this model, we can then contextualize what we expect the quarterback to do versus what the quarterback actually does, and essentially see and contextualize these approaches.
Totally. So this is not our entire feature set. It's way more expansive than this. But these are some of the features. You see the ones that we just talked about. So you have distance off the quarterback's orientation and vision, 5 frames prior that we lagged. You have the receiver velocity vectors that change. We also have quarterback features. So how far they are from the receiver, how long they'd have to make this pass, their movement vector, if they're under pressure or not, just as a 1-0 indicator. And then you also have overall game context last, which is how much time is left. Obviously, that DJ Moore catch, he threw to the end zone because they needed 6 points. They needed a touchdown. And so that obviously matters. So those are some of the features which we included in our feature set.
Yeah, so when applying our model to our example play with PJ Walker, we see that the expected play is really the safe play. So we expect that Steven Sullivan should be targeted and, play to the safe man, get out of bounds, get another shot down the field. But here, because PJ Walker goes for this more unexpected play, we're able to contextualize what PJ Walker does versus what the average quarterback would do in the situation.
So we wanted to check with the eye test, first of all. And so we have the most predictable quarterbacks and the least predictable quarterbacks. Most predictable quarterbacks basically just means they agreed with our model the most. So they threw to the receiver that we predicted to have the highest likelihood for each play. We see at the top, Justin Fields, Ryan Tannehill, Jared Goff, Matt Ryan. These names sort of make sense to be in this category, right? They make good reads and they make safe passes a lot of the time with pretty good accuracy for the most part. Then we have the least predictable quarterbacks. This is really what sort of tipped off the fact that we had maybe done a good job on this, is that Jameis Winston is close to the top. He's second, only to Tua, which we think is maybe just because he's left-handed and we have to basically recode all of that. But Jameis Winston, right, lots of touchdowns, lots of interceptions, makes a lot of unsafe throws, questionable decisions. And so him being in the least predictable category makes a lot of sense to us.
Yeah, so as a toy example for an application of our model, we can essentially find opportunities to optimize quarterback decision making. If we look at yards per attempt between passes following the model versus passes not following the model, as well as completion percentage, we say that we have players here, Jameis Winston, PJ Walker, who find success with more yards on their atypical passes, as compared to players like Marcus Mariota, Teddy Bridgewater, who might find benefits in throwing more conventional passes as they gain more yards, as they're a little more accurate compared with their typical passes versus more unconventional throws.
So overall, just as a quick recap, we were able to model the most likely target using XGBoost ranking model with pretty strong predictive power, around 60%, which we're pretty proud of. Obviously, we could make improvements by incorporating newer factors or more things that we could engineer. If we wanted to look at receiver skill, which would essentially track how well a receiver performs. I think earlier we were talking about like the gravity for a basketball player. So gravity for receivers is another thing that we really would like to include, as well as pre-snap factors. Yesterday, I can make all these ties. Yesterday, we talked about using motion to detect what the coverage is going to be in the defense. And so using pre-snap factors would also be nice to incorporate. We also relied on a lot of proxies. We had to just use that quarterback vision. It's not perfect. It's pretty rudimentary. And there's also a small data set, right? Even for the quarterbacks that threw the most in the first 9 weeks, there were only about 200 throws for those quarterbacks that we could really analyze. And so to be able to model over the course of an entire season would be great, as well as over the course of a career for a quarterback. We could model not only quarterback development, but also in each season if they're doing better against certain opponents or not as good against other opponents.
Yeah. So before we close, we want to thank Dr. Kassam, our outside advisor, as well as our instructor and GOAT Kwong, and as well as CMU Statistics for giving us the opportunity to, spend a summer here, do some research, and present here at CMU. So that concludes the presentation. We'll open the floor to any questions. Thank you.
All right, good job. We do have time for a couple of questions, so please raise your hands. If you have any questions, I'll come to you.
So you guys did you only evaluate the frame at when the quarterback actually made the throw? Did you ever think about how we can evaluate the frames up to the point of making the throw and maybe modeling the decision to not throw to any receiver and take a sack or scramble as like other decision-making outcomes?
Yeah, totally. So for the scope of this project, we looked at the frame of throw, figuring out if they're throwing to the person at that moment that we would expect them to throw to. But we did fit several models that were continuous models, basically, which I think is what you're saying. So modeling from the snap all the way up to the throw and seeing how that changes. That's a more difficult question to answer. It's something that we considered, not in the scope, but it's definitely something that we looked at. Assigning those initial probabilities of do we just let each receiver get equal stake of the probability, like each one, if it's 4, it's 0.25 for each, or if it's 5, 0.2. Trying to assign that was particularly difficult. All right. Thank you.
Hi guys, really good talk. So from my understanding, the big data bowl orientation just feature is based on their shoulders. So the quarterback orientations are probably pretty much always going to be toward the sideline, even if they might be looking downfield. I'm wondering if you guys did anything to account for this, or if you think it probably just decreases the impact of orientation in your model. And if you think future work where we might be able to see their actual line of sight using like data on their head might make your model more accurate and more useful.
Yeah, so definitely. Thank you for asking that question. It's a good question. We did account for this. If we actually go over here, you can see the quarterback vision. We'd expect them to be looking at 90 degrees if they're looking downfield, right? But it's about 115 for like the mode and the median. So we adjusted, I believe it was 30 degrees, just because it made sense and it worked. You can also see it happening here in our model. Definitely once we get that head tracking, and obviously, yes, it reduces the accuracy of prediction if it's in the shoulder, because we're not actually seeing, and on top of, even if you could track where the head is, they'll look with just their eyes, which is also difficult. The more data we get on the head movement and things like that, the more accurate it will be. But yes, we definitely adjusted so that their orientation would be toward the sideline, or not toward the sideline, would be downfield instead of toward the sideline. Yeah.
All right, let's thank the group again. Good job.